Okay, so now we have Oliveira Pinheiro who will talk to us about fluid gravity duality for viscoelastic crystals.
Okay, first of all, thanks for having me here. So this is the title of my talk, and this is based on work that I've been doing with my supervisor Richard Davison. So let me start by giving you some context about viscoelasticity. So when we consider a material that is subject to some deformation like stress, we would classify it as having an elastic behavior if it strains proportionally to the stress. On the other hand, a viscous behavior would be would be when the strain is proportional to the time derivative of the stress, and so in this case the fluid would not be sensible to static stresses. So, however, what we find in our world is this gray area where these two different behaviors couple, and this is the realm of viscoelasticity, a topic that has been studied for quite a while. So the Kelvin-Voigt model and the Maxwell model were two of the first empirical models, and it has been mainly through phenomenological models that this topic has been studied. However, in the last century there were some attempts to describe viscoelasticity from more fundamental principles, namely through the hydrodynamical lens. For example, Eckert in '48 worked with a geometrized notion of strain, and also in the 70s there was some work about the hydrodynamics of crystals, where an elastic behavior is incorporated through the spontaneous symmetry breaking of spatial translations. More recently, in the past decade, there was a lot of studies about holographical models with broken translations, either explicitly and spontaneously, and the need to understand the near equilibrium behavior of these models generated a new interest in having a hydrodynamic description of viscoelasticity free from some of the assumptions of prior works. So some papers answered the need for this description. One by De La Creta and collaborators was proposed some constitutive relations, which however failed when trying to match to some holographic models. Later there was a paper by Grozdanov and Pavlotikul, and however even within the paper they find inconsistencies between their quasi-normal modes and their constitutive relations. And in 2019 there was a paper by Armas and Akash, which until now it has been compared with quasi-normal modes, namely in this paper by Martin Amon and collaborators, and it has been successful. So in my work I will establish fluid gravity duality where a viscoelastic fluid sits at the boundary. From this I'm going to derive constitutive relations, and what I found was agreement with the constitutive relations of Armas and Jane for specific values of the transport coefficients. I also find the spectrum of hydrodynamical modes, allowing us to understand better what went wrong in the paper by Grozdanov and Pavlotikul. And lastly, we find that only for a specific range of a parameter that I'm going to explain later, the theory is linearly stable. So let me start by introducing some of the tools needed to describe crystals hydrodynamically. So I'm going to work with standard crystals. By this I mean with point-like lattice cores in two spatial dimensions. In the continuum limit, this can describe by two form fields, E1 and E2, and I'll keep using like the first Latin letters lowercase to address this internal index. And the way that these form fields encode physical information is through the scalar products between them. So the diagonal elements of this matrix of scalar products will encode compression. So for example, in this case, if we would compress a crystal like this, we should see the norm of E1 increasing, such that the E1.E1 would reveal that compression, and the off-diagonal elements encode shear deformation. So in this case, if we would apply some shear stress, we would see the angle between these vectors change, such that the scalar product E1, E2 would show us that. So by requiring these form fields to be surface forming and also using some freedom of normalization, we can write this as the exterior derivative of some scalar field, and actually this scalar field corresponds to the Goldson-Bozenoff broken translations. We are also going to assume an absence of topological effects, so in this case these locations, and this corresponds to our form fields being closed. So for example, if we are working in terms of the scalar fields, this absence of these locations is trivially realized just by assuming some well-behavior conditions of the scalar field. So from this it's quite easy to see that our crystal has two one-form global symmetries. The way to see this is by building these two-form currents given by the odd star of E, such that J is co-closed, and then by integrating star J over one-dimensional surface, we obtain the topological conserved charges associated to these one-form global symmetries. Okay, so now we want to obtain the equations of motion for our hydrodynamical theory. So besides the symmetric stress tensor associated with Poincare symmetry, we have this antisymmetric current associated to the one-form global symmetry. We can couple these to a background metric and a background gauge field, and then we derive some source conservation equations. So we see that J is conserved, and also the stress tensor is conserved, but only up to terms that vanish when our background fields are flat. Okay, so moving on to the holographic part of this work. So we work with this holographic model with a bulk metric G and a bulk to form gauge field B, with the Einstein Hilbert term with a negative cosmological constant plus a kinetic term for our gauge fields. And let me stress that the one-formal global symmetry at the boundary is realized by the translational gauge invariance of P under a closed two-form. So this theory has a family of Black-Brand solutions given by this isotropic metric with this emblackening factor and this constant strength of the gauge field B. This family of solutions is parameterized by the radius of the horizon and by this constant M, and it's a family that is dual to a family of thermal states of isotropic and homogeneous crystal at the boundary. So in particular, M corresponds to the density of the lattice course. So the main steps on establishing the fluid gravity, well, we considered small perturbations of these Black-Brand backgrounds. Then we solved the equations of motion perturbative and gradient, imposed the ingoing boundary conditions at the horizon, used the holographic dictionary. Let me just note that in this case holographic renormalization requires a double trace deformation that leads to mixed boundary conditions involving a renormalization group scale that I'm going to call curly M. And what we obtained were linearized constitutive relations up to second order invariants. From these constitutive relations we saw a finite bulk modulus B, which has already been obtained because one can compute it from equilibrium. However, more important was the derivation that the bulk viscosity in this model vanishes identically. So I'm not going to show all the constitutive relations, namely the one for the fluxes of the currents J. They are a bit too detailed, but however, on the other side, the fluxes of the stress tensor are quite simple, especially when we turn off the sources. So this way we can see how the shear modulus and the shear viscosity enter the constitutive relations, and we can also see how the tracelessness of the stress tensor is broken by this term involving the RG scale curly M. So we found expressions for the shear modulus and viscosity in terms of a solution to this equation, a solution that is regular at the horizon. So as we can see, the shear modulus involves information about this solution near the boundary, and the shear viscosity in addition also involves information near the horizon. So now that we have the constitutive relations, we can plug them in our conservation equations and compute the hydro modes. So we've used a plane wave nsets, or a wave that is propagating in the x direction, and in the transverse sector we obtained a sound mode, and in the longitudinal sector again a sound mode plus a crystal diffusion mode. So as we saw in the previous slide, we must at some point solve this equation, which we were only able to do numerically, and so what I'm going to show in the following slides are some plots for the coefficients of these modes, and I'm going to show them as a function of the radius of the density of lattice cores over the radius of the horizon, and because we want to keep our temperature positive, the m over Rh is going to range between 0 and root square of 6. So here we have the transverse speed squared of sound for different values of the Rg scale. The black dots here come from the computation by Grozanov and Povotikul, so we can see at least that the quasi-normal modes agree with ours, so as was suspected, the problem comes from their constitutive relations. In addition, we have the longitudinal speed square of sound, which is quite similar, with the important difference that when we send the density to 0 and we decouple the elastic degrees of freedom, we still have a longitudinal mode in the we still have a sound mode in the longitudinal sector. However, when we consider low values of the Rg scale, we see that the speed squared becomes negative, and so we have a linear instability. So I've just noticed that, I mean, this applies to all the speeds, but here I'm showing the longitudinal. So, and actually not only for the speeds, but also for the other coefficients of the modes, we find this that for low values of m, we have negative values of the coefficients, and in the longitudinal sector we have even more. So because of the presence of the speed squared in the denominator of, for example, the crystal diffusion constant, we find some poles for low values of m, even though, as you can see here, the crystal diffusion it's safe for values high enough of our Rg scale. In fact, it was we were able to check that for the entire domain to be safe in all modes, this is the smallest value of m over Rh. Okay, so let me finish by just highlighting once again that this way we have obtained new expressions for the shear modulus, the bulk viscosity, the shear viscosity, and also an elastic dissipative transport coefficient sigma that I didn't mention explicitly, but maybe if you were paying attention, it entered the crystal diffusion constant. We also found the lower bound on the Rg scale that I just mentioned. And some final comments. So a part of this research was also to understand how a regime of momentum relaxation arises when instead of having a finite density of lattice cores, we have a perturbatively small one, such that we are breaking the symmetry not spontaneously but explicitly. And we also investigated the connection with the model by Andrade and Withers. Some open questions are whether we can find bulk solutions that are stable for low values of curly m, and another interesting future direction would be to study holographic models of crystals with dynamical dislocations. So that's all I have to tell. Thanks for your attention.
Is there any questions for Andre? Okay. Andre.
I didn't follow all the details, but the beginning sounds very much like the setup of Penko and Nicolas. Do you have any comments on that?
I don't think I'm not enough familiarized with that. So
Okay, maybe we can talk later.
yeah, thank you.
How do you calculate curly m precisely? Like that value of 15 minus log 3 or...
Oh, okay. So basically we can solve analytically that equation. We can solve it analytically near the zero temperature limit, and we can see that as we increase m, it always happens that the negative values are pushed forward. So by just solving analytically the equation near the zero temperature limit, which corresponds to this part here of the plot, we were able to derive this value. So I think this value, as you can see, so for example for the speeds, this even you don't need it to be this high, but at higher order for the coefficients that are multiplying the quadratic order in k, you need this. But I mean, this is just to be safe in all the domain. One should not discard. Maybe it might be of some physical significance.
I was just wondering, like the curly m had some precise, that boundary limit had some precise significance from any point of view.
I mean, as you can probably see by this log, so it comes from like just the expansion of some arctangent when you solve like analytically that equation.
More questions? I have one.
Yeah.
So you mentioned that you discovered some instabilities here.
Yeah, so I was referring to these linear instabilities. So when the measure.
What do they want to do to the black holes?
So that's not something. I think that's something that I hope to understand better once I address this question, because at least for now I'm just focusing on the hydrodynamical way to see them. But I mean that's definitely an interesting question.
So good. Let's thank Andrea again.